Hey everybody, the day has arrived for the most important theorem that you are going to learn in this class. The fundamental theorem of calculus. A couple things that I want to mention before we get into some of this fundamental theorem. I do want to go over one homework problem from section 4.3. Particularly, it's number 45, so we're going to go over that. Then we'll have some lecture over fundamental theorem of calculus stuff. A reminder that you've got a quiz tomorrow, Thursday, and the quiz is over Riemann sums. So I'm going to give you a couple of functions and have you draw, cut up the interval, write down the rectangles, that kind of thing. I may also ask you some questions about properties. So some of these questions I think are going to be a little easier, but you should plan on at least having to calculate one limit of some sums. So yeah, so that should be on the quiz for tomorrow. So let's go through section 4.3. Let's just do one problem, number 45. I just want to make sure that this was super clear here. I'm going to draw this. Now, my drawing is not necessarily going to do, it's already not doing very good justice. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 1, 2, 3, 4. This is bad. So, all right, so I've got a half circle here. It's negative. Then this goes up and then down with a slope of 1. This is pretty terrible. And then this goes down with a slope of a half here. Okay, so now the problem's asking you to think about, this is -2, -4, 2, 4, 6, 2, and -2. Okay. So the problem asks you to think about how to get the areas under this function. So, for instance, from 0 to 2, you'll notice that it's talking about this area right here. Okay. Well, first of all, it's a negative area because it's under the x-axis, and it's a fourth of the circle. So it should be 1/4 of pi times the radius squared. So that's 4 and that's 4, so those cancel, so the area right there ends up being negative pi. Does that make sense? Okay. Part B, the area from 2 to 6 under the function should be that triangle right there. And that triangle has, it's 1/2 base. The base is 4 times the height is 2. So that area is 4. Got it? No rectangles, no anything. That's not what we're looking for here. We're just supposed to use geometry. Okay, so now, what if I went from -4 to 2? There I want this area plus this area. And so that's going to be the area of the triangle plus the area of the half circle, not a full circle. Okay, the triangle is going to be 1/2 base is 2, and the height is 1, but this is it's a negative height, so you can put the negative there or here. That's a negative area. The half circle is going to be -1/2 of the circle, pi times the radius squared. So this first thing is -1, and the second thing is -2 pi. So that's the area right there. Okay, we're all good so far? And then the area from -4 to 6, well, we did from -4 to 2, that's this. And from 2 to 6 is this, so to get the overall thing, I just add these together. So I take the first from -4 to 2, plus from 2 to 6 is 4, so I'm going to get 3 minus 2 pi. That's my area for part D. Does that make sense? Okay. Part E is maybe a little more confusing. So this is one of the reasons I wanted to take this. Now, absolute value, what the absolute value does, when you take the absolute value of a function, it leaves all the positive stuff there, but takes negative stuff and flips it up. Okay, so in other words, the absolute value function looks like this function. It leaves the positive stuff alone and then takes the negative stuff and flips it up. So if I go from -4 to 6 this way, this part, instead of being negative area, is now positive area. So the area is 1 plus 2 pi. And then this area is still 4. So what you end up getting there is 5 plus 2 pi. Does that make sense? Just taking the negative area and making it positive instead. And then lastly, if I had the area from -4 to 6 under the function plus 2, what they want you to do is separate this out into the area under the function plus the area under the constant function 2. So this we already calculated, that's 3 minus 2 pi. But the area under 2, just the constant function 2, from -4 to 6, well, that's a rectangle of width 10 and height 2. So 10 times 2 is 20. So we're going to get 23 minus 2 pi. Okay? Got it? All right. Hopefully that makes sense. If you've got, I don't think our lecture today is going to take all of the time. So if you've got a few other questions, you are welcome to ask. All right. So today, the fundamental theorem of calculus. All right. Now, different areas of math actually have things called the fundamental theorem. So there's something called the fundamental theorem. So this is section 4.4. Because this is so important, I'm putting it in red. The fundamental theorem of calculus. There's actually a fundamental theorem of arithmetic, a fundamental theorem of algebra. This is the fundamental theorem of calculus. I won't go through those other ones, but okay, now we're going to do this in 2 parts. I don't know why the book decided to do the parts in the order that it did. I'm actually going to, I hope this isn't confusing, but I'm going to reverse the order. So my part 1 is actually the book's part 2, and my part 2 is actually the book's part 1. My advice, the book really tries to do this in generality. It kind of makes it not that clear, unfortunately. So my advice is to stick with what I'm about to present to you and kind of take what's in the book with a grain of salt. You're welcome to look at it. But my advice is that what they're doing there is fairly confusing. They also introduce the mean value theorem. They develop a mean value theorem for integrals. That's a lot of material to have in one section. And it kind of distracts from the most important thing, which is the fundamental theorem of calculus. Okay? So here is, to kind of motivate where we're headed here, we're going to do a couple of examples. Part one here is not going to be that impressive. It's going to be kind of strange. I think you're going to go, that's weird. I wonder why that works. But the kinds of problems we're going to be doing in part 1, you're going to be like, yeah, those are really weird, contrived problems. But doing part 1 is going to give us part 2, and part 2 is the payoff. Part 2 is what's going to make our world of finding definite integrals so much easier. It's going to be a whole lot easier. Okay. So I want us to calculate, first of all, the area from 0 to 1 under the function 2t plus 1 dt. One thing I immediately want to say is that you should remember that because I'm going from a number to a number, the result of this is going to be a number, and so it doesn't matter whether I use 2x plus 1 dx or whether I use 2 squiggle plus 1 d squiggle. Okay? None of that matters. All of these are going to give me the same answer. There's a reason that I'm using t, and you'll see why in a little bit. So for now, I'm going to just stick with using t, but you can imagine it being x if that helps you. Okay, so what this means is if the area under the function 2t plus 1, so let's graph that. So here's my function, 2, 3, 4. Okay, that's okay. Okay, so I'm going to go from 0 to 1. All right, so I want that area right there. Let's actually just calculate it, okay? So I'm going to break it into a rectangle and a triangle. The rectangle has area 1, and the triangle has area 1/2 base 1 times height 2, so this overall is going to be 1 as well. So the overall area there is 2. Not too hard. Okay? So now I'm going to say, okay, well, instead of wanting the area from 0 to 1, I want the area from 0 to 2. And you say, okay, no problem. I got this. So let's, instead of going from 0 to 1, we're going to go from 0 to 2. All right. So now we've got a rectangle. The bottom rectangle down there has base times height is 2. And the overall triangle that's above is going to be 1/2 base is 2 times the height. Well, when I go over 2, I go up 4, so that's going to be 4. So I get 2 plus 4 is 6. Not too hard. Okay? All right, now I'm going to be annoying, and I'm going to say, well, that's great, but now I want the area from 0 to 4. And this is where you start to get tired of me, and you're like, ugh, please stop. But let's do this one more. Okay, so if I go from 0 to 4, that's going to be, I'm going to get some triangle big thing, right? And it's going to be a rectangle plus a triangle. So the area of the rectangle is still going to be, it's going to be 4. And then the triangle is going to be 1/2 base is 4 times the height. Well, if I go over 4, this thing has a slope of 2, so I'm going to go up 8. And so I get 4 plus 16 is 20. Okay, and then annoying little me comes along, and then I say, okay, that's great, but now I want it, and you go, stop. If you want the area from 0 to something, I'm just going to calculate that for you, and then you can fill in whatever you want. Okay, this is the beauty of mathematics, is that we can do things in general so that we can solve lots of problems all at the same time. So to keep the annoying me from pestering you, what we're going to do is we're going to go from 0 to some number that I'm going to call x. And then later you can fill in x. It's going to be at some area that depends on x. And later you can fill in x. So x could be 1 or 2 or 4 or 16. I'm going to stop pestering you because you just gave me a formula. And then I can fill in whatever I want. Okay? So let's do that. So if I wanted the area from 0 to some amount x underneath this function, I want that area right there. It's still going to be, notice that I had to use a different variable than what I have kind of as my general variable here. Those mean different things. That's why I'm using an x here and not an x here. I'm still going to break it apart as a rectangle and a triangle. The rectangle here is going to have, it's going to have length x and height 1. And then the triangle is going to be 1/2 base times height. Now the base is x, and the height, if I go over x, because this has slope 2, I'm going to go up 2x. So you'll notice that the half and the 2 cancel, so I get x squared from that from this term right here plus an x from this term. That is the area going from 0 to x. So now I can't bother you anymore. If I want the area from 0 to 10, you just tell me plug in 10. It's 100 plus 10. If I want the area from 0 to 1,000,000, plug in 1,000,000. If I want it from 0 to 3, plug it in. Okay, so you just calculated it in general. And again, that's the power of mathematics, that we can do things in general so that later we just have to plug in to get our answers. Here's the thing that I want you to notice, though. First of all, it's a function of x, because if x is 4, that's going to be a different area than if x is 2 or if x is 1. So this is a function of x. Notice I don't have two numbers here, I have a number and a variable. Okay, so this is a function of x. But what do you notice about, do you notice any relationship between that function and that function? Just think about that for a second. Do you notice any relationship between the resulting function that came out and the original function that I started with? Think of an x here instead of a t. What's a relationship here? Okay. One thing that you'll notice is that if I differentiate this function, what do I get? I get 2x plus 1. And lo and behold, that's actually that function right there. Wow. Who knew that areas, now remember the derivatives don't have anything to do with area, they have to do with slopes of functions. So in other words, I took an area under a function, and then I took a slope of a tangent line, and for some reason I ended up back at the original function that I started with. Okay. So this leads to this is actually the first part of the fundamental theorem of calculus. Okay, so this is the fundamental theorem of calculus, part 1. So let's let f be a continuous function on a closed interval from a to b. And then let's define the integral from a to x under the function. Now I have to use a different letter here. So I'm not going to write f of x dx, I'm going to use f of t dt. But I'm going from a to x, and I'm assuming x is between a and b. So the area from a to x under this function, I'm going to call that area, this area right here is capital F. Notice that capital F gets bigger as x gets bigger, and capital F gets smaller as x gets smaller. Okay? Just like this function, this area function. This is an area function. Okay, then the derivative of the area function is the original function with x plugged in. Okay, if I take an area function and I differentiate it, I get the original function back. That should be very, very surprising. Okay, what that tells you is if I take a function and I get an area, and I take its area to get another function, and when I differentiate, I get back to the original function again. So in other words, this is kind of telling you, so if I do this step 1 and this step 2, this is telling you that differentiation undoes integration. In other words, it suggests that they're opposites of each other. Okay, in order to be opposites to each other, it has to work both ways. If you differentiate and then integrate, you have to get back to what you started with too. But this is suggesting that finding areas and finding tangent lines are actually very closely related. In other words, they're actually reverses of each other in some way. Okay. So what I'm going to do is prove this. And then I'm going to show you some of the types of homework problems that this is actually going to work itself out with. Okay. And the proof is actually not that hard, surprisingly. It's actually really, it's a really nice, nice proof as long as you think of it visually, okay? Okay. So let's go back to, I'm assuming that we have a continuous function on a closed interval. And let's take this function capital F from a to x. Okay. What I want to do is prove that the derivative is the inner function. Okay. Now, before, when we were doing derivatives and we were doing derivative proofs, one of the very first things we would start with is the definition of the derivative, and that's what we're going to start with here. So the derivative of f is, and now I'm going to ask if you remember the derivative definition. I'm just going to give you a minute to see if you can remember that. If I give you a function, so f of x, and I say, what's the derivative? There was a limit and there was an h involved somewhere. Do you remember that definition? So you should be saying something like, the limit as h goes to 0, there should be a fraction here. Okay, remember? Should be f of x plus h minus f of x all over h. Okay? All right. So let me actually draw this. I want to keep that statement for a second. So let me do my best to draw this in here. Okay, here's A, and here's X. Okay. And this area right here, this is little f, this is capital F of X. Okay, the area from A to X. Okay, so my limit definition says f of x plus h minus f of x, and then it's all over h. So let's actually fill in what this means. So f of x, this part right here means the area from a to x under the function. This thing right here means the area from, so f of 2 would mean the area from a to 2. F of 5 would be the area from a to 5. F of x plus h is the area from a to x plus h. Okay, so in other words, if I had x plus h here, this first term actually represents this area, and the second term represents this area. Does that make sense? All right, well, if I have this area minus this area, you can probably guess what I'm about to write next. This area minus this area is going to be this middle area. So that's going to be the area from x to x plus h under the function. Okay. So in other words, this area. All right, so I need to take that area in red and divide by h, which is actually the width of the area right there. Now I want you to think, what's our goal? We want this derivative to equal what? We want it to equal f. But the thing I want you to realize, you can actually kind of see that's coming geometrically because we have an area that's almost like a rectangle. It's not quite a rectangle, but it's close. It's an area. And if we take the area and divide by the width, if it were a rectangle, and we took the area and divided by the width, we would actually get the height. And the height is basically f of x. Right here's x, and when I plug x in the function, I get f of x. So height times width really is area. So if I take the area divided by the width, this should equal the height. And that's just what we need to prove. Okay, but conceptually, hopefully you can see that. The area divided by the width is going to be the height, basically the height of the function. Okay, so in order to get this, we're gonna have to get a little bit technical here. So I'm going to take this and just expand it out a little bit more. So I'm going to have the interval from x to x plus h. Okay, this is that area that I have in red there. Okay, make this a little more obvious, just so, because it doesn't have to be really nice in between right now. So this width is h. Here's what I'm going to do. I'm going to identify now. For this, I'm going to put this problem aside just for a second. And I want you to notice that if I find the highest point on this, let's say the highest that this function gets in this rectangle right here, we're going to call the highest point capital M. And the lowest that this function gets, I'm going to call that little m. So that's the smallest and the biggest that the function gets. Okay? Here's what I want you to notice. The area that we're interested in, this area right here. Okay, so notice that the area from x to x plus h, the worse that is, that area is less than this rectangle area, which is the maximum the function gets, times the width. Okay, this rectangle is capital M times the width, M times H. But it's bigger than the smallest the function gets, times the width. Okay, let me say that again. If I take on the interval, if I take the highest point, call that capital M, and draw in a rectangle here, the blue kind of adjustable area is definitely less than or equal to this, the rectangle where I'm taking the maximum height. And it's bigger than or equal to the rectangle when I'm taking the minimum height. Okay, in other words, if I take the minimum height and draw a rectangle, that's what I get. Now here's where this is going to be nice. Let's divide everything through by the height h. Because I want this thing, and this thing has the area divided by h. So if I divide this by h, I just get little m. If I divide this by h, I get this. If I divide this by h, I get big M. Can you guess what I'm about to do? I want the limit of this thing, so let's see what happens to this thing and this thing when h goes to 0. When h goes to 0, we're squeezing this thing over, we're squeezing this rectangle in. When we squeeze that rectangle in, the highest point eventually squeezes over to this height right here is f of x. So eventually the highest point, when I squeeze this interval in, it doesn't have that point anymore, it doesn't have that point. Eventually the highest point goes to f of x. And eventually the lowest point when I squeeze h in eventually also becomes f of x. So, by the squeeze theorem, this thing right here when h goes to 0 also goes to f of x. Okay? Cool. So this is actually true. Fundamental theorem of calculus, part 1 is actually true. If you integrate from a number to x and then differentiate, you get the original function back. Okay? So So let's look at a couple of, that sounds really theoretical. Let's look at a couple of examples. So if you've got your textbook, go ahead and open it to section 4.4. And I've got a homework sheet that Ms. Barabo is going to pass out. For next week on Monday, you've got homework problems due from section 4.4 that are over both the first part of the fundamental theorem of calculus and the second part. The first part, because the book switches them, my first part ends up showing up in later problems, so I ordered them. When you get that sheet, you'll notice it'll say Fundamental Theorem of Calculus Part 1, and the numbers will start 81, 82, 84. Okay? If you want to do this homework tonight, you don't have to do it tonight, but if you want to work on it tonight while it's fresh, you want to work on the problems that are in the 80s and 90s. Tomorrow's material that we go over is going to go over the earlier problems. Does that kind of make sense? So let's do, I'm going to erase this proof here, and let's go over a few of the homework problems. Okay, so let's take a look at number 83. I'm not going to do homework problems, but on page 286, I'm going to look at, you've got 81 and 82 on your homework. I'm going to look at 83, okay? So here's what they want you to do. So we've got a function f of x that on 83 is written as the area from -1 to x of this function. Square root of t to the 4th plus 1 dt, okay? So I took, think of this, if you want to kind of mentally think of this is your f of t. And what they want you to do in these problems, it says use the second fundamental theorem of calculus, that's for me, FTOC part 1, to find the derivative. Now what the theorem says is if you have an area set up this way, the derivative is just the inner function with x plugged in instead of t. So what you're supposed to do here is you take the inner function, which is this thing, and you plug in x instead of t, and you're done. That is problem number 83. That's all. Okay? Shocking. Not too bad, right? Okay, let's take a look at number 85. Number 85 says you've got the function f of x is the area from 0 to x under t cosine of t dt. Okay, and it's asking you what is the derivative. It's not asking you to calculate this actual function. Figure out what the area under this function is. Don't do that. It's just saying what's the derivative of that area. And the derivative of the area, what we do is we take this function, and everywhere where there's a t, we put an x. That's it. That's it. Got it? Okay, a couple things I want to note. First of all, you'll notice that I did nothing with this -1. I also did nothing with the 0. Okay? One of the things that you'll notice in the fundamental theorem of calculus is that this a never shows up in the derivative. Okay? It actually doesn't matter. It matters a little bit, but not really. This number that's down here does not matter when you're actually taking a derivative. If you were doing the calculation itself, it does matter. But when you take the derivative, it turns out not to matter so much. Okay? Does that kind of make sense? Well, I don't know if it makes sense, but that's a result of the fundamental theorem of calculus. To help you kind of see that, maybe, let me show you something here. Do you remember that when we did from the area from 0 to x under this function? This was what I started out with. That ended up being x squared plus x. And then when we differentiated that, we got 2x plus 1, which was the original function with x plus 1 plugged in, okay? Let me do, just to sort of show you, to put your mind at ease so you can see an example of this, let's do the area from 1 to x under that same function, just so you can see how this works if the number on the bottom is different, okay? Just to kind of give you a rough idea of what's going on here. So this would be the function from 1 to x, okay, and it's the function 2t plus 1, so I'm going to start at a y-intercept of 1 and go up 2 over 1, up 2 over 1, etc., okay? So I want this area from 1 over to x. Okay, I want this area right here. We're doing this in using geometry in a very specific way, so you can kind of get a little more confidence that theorem actually does work, and that this number down on the bottom actually doesn't show up in the derivative, okay? So if I were to actually calculate this area by hand, not using rectangles, but actually just using geometry, I have a rectangle here and I actually have a rectangle here and then a triangle up here. So let's first calculate the rectangle. The rectangle has width x minus 1. And notice that the height, you have to start here. We started at 1 in this original thing, but if we're starting at 1 here, we have to go up 2 over 1. We're starting at a height of 3 here. So this rectangle right here has a height of 3 and a width of x minus 1. Got it? Plus, the triangle has 1/2 base times height. The base, again, is x minus 1. And the height, well, every part that I go over, I'm going to go up twice that. So I'm going to go up 2 times x minus 1 if I'm going over x minus 1. If I were going over 3, I would go up 6. If I'm going over 4, I'm going to go up 8. If I'm going over x minus 1, I'm going to go up 2 copies of that. So that means, let's cancel some things. If I multiplied this out, let's multiply it out, we get 3x minus 3 plus, let me square this out, x squared minus 2x plus 1. So let's combine some things. So we get x squared plus 3x minus 2x is plus x. Then minus 3x plus 1 is minus 2. I want you to compare the area function from 0 to x and the area from 1 to x. Okay. The difference is actually just this area from 0 to 1, right? If I go from 0 to x, that's the same thing as going from 0 to 1 and then 1 to x. So the difference is just this constant area. So now when I differentiate, that constant goes away, and I just get 2x plus 1, which is, again, the same thing that I had originally. So hopefully this should kind of assure you that the number, when I'm differentiating, that number that's in the bottom actually doesn't matter. It doesn't matter what is sitting down there. Does that make sense? Okay. Before I do, there's a couple of other homework problems that I want to do, and then we'll be done. One other thing that I want to point out here is that if I start, one thing that you should see from this diagram is if I start with any continuous function and I do this area function, differentiating gets me the original function back. So in other words, any continuous function has an antiderivative. Okay, let me say that again. All continuous functions have antiderivatives. Have antiderivatives. Now that doesn't mean you could have some kind of crazy continuous functions that doesn't mean we can always write a nice formula for the antiderivative. The antiderivative, we can write an area function, that's going to be an antiderivative. But that doesn't mean there's a nice formula for this. Okay, but every continuous function always has an antiderivative. I want to drive that home into your brain. If you start with any continuous function, could be absolute value, could be some other weird types of continuous functions that we've seen. All of those have antiderivatives. Okay, we've seen one right here. If you make an area function, then when you differentiate, you get the original function back. Okay, file that away in your brain. That's an important thing to remember. All continuous functions have antiderivatives. Please write that down. Okay. All right. I now want to show you, let's skip to number we'll just do a couple more examples and we'll be done today. Okay, we're good on time. All right, let's look at number 91. This is, so here my function is the area from 0 to x squared under sine of t squared dt. Okay. Now I want you to take a look at this problem just for a second. And how is this problem different than other problems that we've been doing before? Than the other two that I put up here. Notice that this is not x, it's actually x squared. Okay, so if this were the area from 0 to x under sine of t squared dt, then I could differentiate really easily by just slapping an x in here and using that. But now I have x squared instead of x. So in other words, I have a function, this function, sine of t squared dt, from 0 to x, and then inside of it, I've stuck in x squared. Inside should be a trigger point for some sort of rule that we have related to differentiation. Should be the chain rule, right? If I stick one function, in other words, I'm sticking x squared inside of this function, there's a way that I go about doing the derivative, okay? So let's formalize this a little bit. Our outer function here is this function, the integral from 0 to x of sine of t squared dt, and my inner function is x squared. I'm sticking x squared inside that function. So according to the chain rule, what I do is I do derivative of the outer. So the first thing I'm going to do is focus on what is the derivative of this outer function. Well, the way that I would do that is I would just stick in an x wherever there's a t. Now I'm doing the chain rule, so instead of writing x, I'm writing parentheses. This is the derivative of this outer function. Got that? My outer function is this. Its derivative is very simple. I just take an x and stick it where the t was. So that's derivative of the outer. Now I just stick in the inner and multiply by the derivative of the inner. In other words, it's going to be sine of x to the fourth times 2x. That is my derivative function. Okay? Let's try this with another example. I'm not going to use one of them there. I'll make up another example here. Let's suppose I have the function that's the integral from 1 to e to the x of tangent squared of square root of t dt. Okay? Kind of crazy. Okay, if this right here were x, we would be good. The answer, the derivative answer, not the function, but the derivative would be tangent squared of square root of x. That would be the derivative. But that's not what we have here. Instead of having x, we have e to the x. So we have an outer function of the area from 0 to x of this crazy function. And then instead of x, I'm throwing in e to the x. So what I'm supposed to do here to get the derivative is I take the derivative of the outer, and the way I take the derivative of the outer is I take the original function, but instead of t, I put in x, right? So I would write tangent squared of square root of x, but I'm doing the chain rule, so I'm going to write parentheses there. Then I plug in the inner, and I multiply by the derivative of the inner. So in other words, it's tangent squared of the square root of e to the x times e to the x. That's my answer. You'll notice after you do a few of these problems that all you're doing is instead of taking x and putting it in here, you're taking the function and putting it in here, but then you're multiplying by the derivative of the inner of that function. Okay? So that's one thing. Okay, one more example that I want to point out, because number 88 is a little funky. So let me do number 87. That'll be our last one today. So number 87 says, let's do the area from x. So my function, f of x, is the area from x to x plus 2 under the function 4t plus 1 dt. Okay, how is this different than what we've done previously? Notice that now that's not a constant anymore. If that was from 3 to x plus 2, what I would do is I would just write down 4t plus 1, but instead of the t, I would throw in x plus 2 and multiply by the derivative. I'd use the chain rule the way we're doing over here. But that's not a constant on the bottom, and that messes it up. So here's what we do. There's a little trick we're going to use here. Instead of writing from x to x plus 2, I'm going to go from x to 0, and then from 0 to x plus 2. This is using a area rule, that the rule for the definite integral that we have seen before. If you go from a to c and then from c to b, that's the same thing as going from a to b. But the nice thing about this is that I now have a constant in the bottom on this integral, and I can do this the way that I was doing it normally before. Okay? This one's kind of messed up, but the way that we fix it, because the constant always has to be on the bottom. The constant is always on the bottom here. You see that? The way that I get the constant on the bottom is to flip it. Oops, 4t plus 1. But if I flip it, I also had a rule for that. That if I flip it, I have to put a negative sign on there. Okay? All right. So here, my function is now in a place where I can actually take its derivative. Okay? So what I'm going to do here, I just have a constant on the bottom and x on the top, so this is going to be very easy. What I do is I just take the original function, but instead of t, I write x. Okay, so that's the derivative of this area. It's not the area itself, but it's the derivative. Plus, now I'm going to do this one, but instead of going from 0 to x, it's 0 to x plus 2. So I actually have an outer function here that's from 0 to x, and then an inner function that is x plus 2 stuck in there, right? So what I'm going to do is derivative of the outer, 4x plus 1, plug in the inner, x plus 2, and then times the derivative of the inner, but the derivative of the inner is just 1. So that is my derivative here. So it's negative 4x minus 1 plus 4x plus 8 plus 1. And what we'll notice here is that the 4x's cancel and the 1's cancel, and I just end up with a derivative of 8. Okay? Makes sense? All right, so if you end up with two things here that are both variables, you have to split it So that and there's no reason that I particularly chose 0. I could have put a 1 here in both cases, or a 3. As we saw before, when you differentiate, you're not using that bottom number, so it doesn't ever show up anywhere. Okay? So if you've got some extra time there in class, take a look at the homework, and Ms. Baribeau can answer your questions. Thanks so much, and we will finish up the fundamental theorem of calculus tomorrow with the most powerful part of it. This may seem a little contrived, but the most powerful part of this theorem is what we're going to see tomorrow, and it's going to make your life so much easier. We'll see you tomorrow.